Okay, chapter 2 is about radical functions. 2.1 is radical functions and their transformations. So just like the transformations that we did in the first unit on basically a general overview of linear and quadratic and all of the other ones, this one's just going to focus a little bit more on the radical just on the radical functions. When we're doing these transformations, the same rules apply as it did in the last chapter, where you have your h and k values that are going to move it left and right or up and down, and then your a and b values, which are going to either expand it or condense, not the right word, but your graph based on where it lies on the x and y planes. So a radical function is a function that involves a radical with a variable in the radicand. So normally a radical is just square root, cube root, or whatever. A radical function has a variable with it. So y is equal to 3x and y is equal to the cube root of 4x plus 5 are both examples of a radical function. So the first thing we want to do here is just do a graph of a radical function. So we're going to sketch the graph of y is equal to square root of x plus 5 using the table of values, and then when we're done we'll state the domain and the range. So in my table of values, I'm going to put a couple of negatives and positive and 0. So I can use negative 5 because negative 5 plus 5 gives me 0, and I can square root of 0. I won't go larger than negative 5 because smaller than negative 5, like a negative 6 or even a negative 10, because I'm going to have a negative under the square root sign, and I can't do that. So if I tried negative 5, negative 1, which will give me a 4, square root of 4 is 2, so you can see I'm kind of selecting my numbers so that I get perfect values underneath there instead of decimal. Negative 4 gives me a value of 1, which is square root of that is 1, and if I try 4 plus 5 is 9, square root of that is 3. So if I graph this, I'm just simply plotting my points. Just label my axes. Negative 1 and 2. Negative 4 and 1. And 4 and 3. So you can see my graph is looking like that. My non-transformed graph, or my base function or my principal function, would be y is equal to square root of x. I'll do that one in red. So y is equal to square root of x is just going to be at 0, 0, 1 and 1, 4 and 2. So I'm just taking square roots in my x value, so I'm picking perfect squares. So then I could use 9. So it would be 9 and 3. Like that. Oops, did I not go high enough with that? Oh, my blue graph here, I should have curved it up a little bit more. And I'm just going to do that so it's not so confusing for you later. So this should have gone more up like that. Okay, so my base function, or the parent function, that was another word that we used in the last unit, would look like that. So for y is equal to square root of x, my domain for this one would be the set of values for x, but x has to be greater than or equal to 0, and for both of these we're looking at elements of real numbers. My range then, again, I didn't go below the y for my red graph, so it'll be y is everything greater than or equal to 0. For the blue graph, for y is equal to square root of x plus 5, my domain is a set of values for x such that x is, so I'm going everything larger than or equal to -5. And my range for this function, it didn't change. I'm still on that x is equal to 0. I'm on the 0. Or sorry, y is equal to 0, and I don't go below it. So you'll notice that that 5 in the Radican moved my domain 5 to the left. So that positive 5 in the Radican moved my domain and the graph. Move the whole thing 5 to the left. Okay, graphing radical functions using transformations. So you did a little bit of this in the last chapter. We just kind of touched on it just to show you about transformations. So it says you can graph a radical function of the form y is equal to a square root b times x minus h plus k by transforming the graph of y is equal to square root x based on the values of a, b, h, k. So basically what it's saying is you have your parent function of y is equal to square root x. When you apply transformations of a, b, h, and k, you move your graph and you can change the shape of it slightly. So it says the effects of changing parameters in radical functions are the same as the effects of changing parameters in other types of functions. So basically what you did in chapter 1 still applies here. So parameter a results in a vertical stretch of the graph y is equal to square root x by a factor of absolute value of a. So if a is less than 0, then the graph of y is equal to square root x is reflected in the x-axis. So all that's saying is if I have a negative value in front of here, it's going to flip my graph in the x-axis, and it flips it over that x-axis. It's going to stretch it vertically, so it'll either, depending if a is a fraction or not. If a isn't a fraction, it's going to stretch it, and if it is a fraction, it's going to shrink it. Parameter b results in the horizontal stretch of the graph y is equal to square root x, so it affects the x value by a factor of 1 over the absolute value of b. So if b is less than 0, the graph of y is equal to x is reflected in the y-axis. So the first part is saying your horizontal stretch is affected by 1 over whatever the b value is. So if b was a 2, your horizontal stretch factor will be 1/2. If b was a negative value, then your graph is going to reflect and it's going to flip over the y-axis. H determines the horizontal translation. If h is greater than 0, the graph is translated, I lost my spot, to the right h units. If h is less than 0, the graph is translated to the left, absolute value h units. So h is greater than 0. If it's a positive value, once you pull it out of there, then you're going to have a right transformation. If it's less than 0, it's going to go to the left. But that's once you've pulled it out of the equation. So you don't take it for what it is in here. You pull it out and you say h is equal to either a positive or negative. Parameter k determines the vertical translation. If k is greater than 0, the graph goes up k units. If k is less than 0, then the graph is translated down, absolute value of k units. So positive up, negative down. Nothing different there from last time. Okay, so it says sketch the graph of the radical function y is equal to -2 square root x plus 3 minus 1 by transforming the graph of y is equal to square root x. So we'll do our original graph first, and then we'll do the transformations. And I want you to do these transformations using that table of values. And if you are using the table of values, then that way you are going to keep track and make sure you've done them in the right order. And you can do them all in one step, or you can break them up. I'm going to show you them kind of in one step, and then if you wanted to do it broken up, then you can do it that way. So in our original graph, if it was y is equal to square root of x, we'll do that one in blue. Your x and y values, so if x is a 1, y is 1. If x is, and I'm going to pick perfect squares, if x is 4, y is 2. If x is 9, y is 3. If it was 0, it would be at 0. So my graph is 0, 0, 1, 1, 4, 2, and 3, 9. Okay, so again, that is my parent graph, or the regular graph. So if I take a look at -2, y is equal to -2 squared x plus 3 minus 1. My a value, a is always, because this is the original, or this is the that's my transformation. So my a is equal to -2. My b is equal to 1. My h is equal to -3. And my k is equal to -1. So that means in my transformed graph, and I will do that one in, I'll do it in red. So if my original x value was a 1, that means I have to apply x over b, and then plus my h, and it's my a times the y plus the k value. Because remember, a affects the y, and k affects the y, and b affects the h, or sorry, b affects the x, and a affects the h. And your b value is always done as 1 over b. So that's why I have it as x over b. I could have written it as x times 1 over b. Means the same thing. So for my x value, it was a 1. My b value is a 1, so 1 divided by 1 is just 1. Plus my h, which is -3. So then that means it's going to be at sorry, I lost my train of thought. 1 minus 3, so it's at -2. My y value was at 1, so I go 1 times -2 is -2, minus 1 is -3. So my 0.11 is transformed down to -2, -3. So 4. 4 divided by 1 is 4. 4 minus 3 is 1. My 2. 2 times -2 is -4. -4 minus 1 is -5. For my 9, 3, so 9 divided by 1 is 9, minus 3 is 6. And then for the y value, it was at 3. 3 times -2 is -6, minus 1 is -7. And what's my last point? 0, 0. So 0 minus 3 is -3. -2 times 0 is 0, minus 1 is -1. So that's the transformation of all of my points. So these have transformed, so all I did was take my 1, I divided by 1, subtracted 3. For the y, I multiplied it by -2, and then I subtracted 1. So now my transformed graph is going to look like this. So my point was at -2, -3, 1 and -5, 6 and -7, and -3 and -1. I lost my, there we go. So now it's going from there to there. So I can check even just my transformations, my left or right. This one was at 0, 0, and it should have moved over -3. So 1, 2, 3, so you can see that's right. And it's gone down 1. So my transformation is all right there. So now the B part says identify the domain and range of y is equal to square root x and describe how they are affected by the transformations. So in the original question, this is the same as it was in the last one. Our domain is a set of values for x such that x is greater than or equal to 0, and our range, set of values for y such that y is greater than or equal to 0. So our domain in the red graph now has translated 3 units to the left. Which is the equivalent of our h value. Our range has gone and translated 1 unit down, which is the equivalent of the k value. So h is going to affect the domain, and k is going to affect the range. So now we can take a look at a graph and find the equation by looking at the a values and the b values, as well as your horizontal and vertical translations. So it says a radical function that involves a stretch can be obtained from either vertical stretch or horizontal stretch. Use an equation of the form y is equal to a square root x or y is equal to square root bx to represent the image function for each type of stretch. So it says Maylene is designing a symmetrical pattern. She sketches the curve shown and wants to determine its equation and the equation of its reflection in each quadrant. The graph is a transformation of the graph y is equal to square root x. What are the equations of the 4 functions Maylene needs to work with? Okay. So what we want to do, this is the graph that she came up with. We want to give it an equation so that we reflect it in each of the quadrants. So we want an equation for when it's here in quadrant 1. We want an equation when it's in 2, 3, and 4 if we were to put the reflections on there. So I'm just going to switch to this one, or to the next one. So it says superimpose the graph of y is equal to square root x and compare corresponding distances to determine the factor by which the function has been stretched. So if we want to take a look at the vertical stretch for this, our original equation here is in red, and black is that transformed equation. So if we take a look on this equation, so this is the y is equal to square root x here. So that's the parent equation, or the base equation. So normally our first point was at 1, 1. But our first point where it crosses on the transformed equation went up to 2. So we went 1 over and 2. So the horizontal stayed the same there, but our vertical was up by a stretch of 2. So remember, y is equal to the a value is our vertical stretch. So it says this represents a vertical stretch by a factor of 2, which means a is equal to 2, and the equation of y is equal to 2x represents the function. So that represents the function with a vertical stretch. We can write that, though, with saying it had a horizontal stretch instead. It'll give you the exact same graph, but we're just going to move and work with the b function instead of the a. So in our original graph, the first point, do I want to use the first point? Well, this point here, because if I look at it here, it's at 1, 1, and there was at 1, 2. And you can figure it out from that one, but it's easier if you take a look at this point here. So this point here occurred at 1, 2, 3, 4, and 2. So this is 4 over and 2 up. And in this graph, if I look at the over, it went over 1. So this went over 1 to get to that first spot, and this transformation here went over 4. So it says each horizontal distance is 1/4 the corresponding distance for y is equal to square root of x. So if I want to take a look at, when I'm looking at it, I have to look at the ones that are on the exact same x point. So this point here and this point here are sorry, not the same x, on the same y point. So that's why I take a look at those. So this one went over 1, and the next one went over 4. So it says this represents a horizontal stretch by by a factor of 1/4, which means b is equal to 4. So the equation y is equal to square root 4x represents the function. Okay, so my graph stretched from going, in the original one it went over, in my original one it went over 4, but in the transformed it went over only 1 point. So this one, when you're looking, I'm just going to go back to the first one, the vertical, it went up 2, but in this one, it went up 1, but in the other graph, so where it's in a line, okay, and this one's in a line, it went up by 2. This one, it went over by 4, which means it's a factor of 1/4, but that means your b is a 4, because this is always 1 over b. So when you put that into your equation, your b is equal to 4, so it becomes square root of 4x. So you can express an equation as either a vertical or a horizontal stretch, and if you take a look at this, square root of 4x, well, square root of 4 is 2. So that just equals y is equal to 2 square root x. So they both are exactly the same. One is just simplified. So it says express the equation of the function as either y is equal to 2 square root x or y is equal to 4 or square root of 4x. So you can express it either in a vertical stretch or a horizontal. A second way to do it, so this way was using the graph and basically counting your spots. The second way to do it is to find the points and use the coordinates to find your new calculation. So it says use the coordinates of one point on the function, such as 1, 2, to determine the stretch factor. So if I substitute 1 for x and a 2 for y in the equation, y is equal to ax. So just so you see where I got this from, this is from this point here. So on my stretched graph, I went over 1, up 2. So this is the point I'm looking at. So when I substitute that into y is equal to ax, my y value is 2, my x value is 1. When I solve, I get 2 is equal to a. So if I want to view that as a horizontal stretch then, so that was for the vertical. So using that coordinate 1, 2, and I substitute it in there. So I have y is equal to square root of bx, 2 is equal to square root of b times 1, so 2 is equal to square root of b. To solve for b, I square both sides, so I have 4 is equal to b. So you can either do it by counting or by picking the point and seeing how it changed from the original equation. Okay, so then it says, represent the function in simplest form, k. Y is equal to 2 square root x, or by y is equal to square root 4x. So either way, again, when I simplify them, I get the same equation. Or if I expand it, I get the same equation, or the same function. So it says, determine the equations of the reflective curves using y is equal to 2 square root x. So remember, the first one said that we want to do it so that it's reflected into the other quadrants. So reflection in the y-axis results in the function y is equal to 2 square root of negative x, since b is equal to negative 1. So if we want that to be the reflection in the y-axis, so basically this was the graph we drew, this reflection to square root of negative x means that I'm going to flip it in the y over the y-axis. So that's going to be this graph. A reflection in the x-axis results in y is equal to negative 2 square root x, and a is equal to negative 1. So that would be this one. So that means if I want it here, I'm going to have both of them negative. Negative 2, my a needs to be negative, and my b needs to be negative. So it says reflecting, that's this part right here, these graphs into the third quadrant, results in the reflection y is equal to negative 2 and a negative x. Okay, so depending on if you want to view it as a vertical or horizontal stretch, this is just all it's doing. So your original equation, y is equal to 2 square root x, y is equal to 2 negative square root x, x is going to be in quadrant 2, y is equal to negative 2 square root x is going to give you quadrant 4, and y is equal to negative 2 square root negative x is going to give you quadrant 3. Similarly then, so that's doing the verticals. If you wanted to use the horizontal stretch factor, then you would be switching that to square root 4x, square root negative 4x, negative square root 4x, and negative square root negative 4x. So same thing. This first one would be in excuse me, quadrant 1. This one would be quadrant 2, quadrant 4, and quadrant 3. Okay. Determine two forms of the equation for the function shown. The function is a transformation of y is equal to square root x. So show algebraically that the two equations are equivalent, and then what is the equation of the curve reflected in each quadrant. Okay, so the first thing that we're going to do is we're going to determine the equation of this transformation. So I'm going to use, instead of doing the graph of y is equal to square root x and putting that on there and then counting the points, I'm just going to use the calculating using the coordinate. So if I use this coordinate here, which is at 1 and 1/2. So if I'm going to do the vertical stretch then, y is equal to 1/2, that equals a square root of 1. So 1/2 is equal to a. So this equation would be y is equal to 1/2 square root x. So that's showing the vertical stretch. If I wanted to show it with the horizontal stretch, not a, but y is equal to square root of bx. So I have 1/2 is equal to square root of b times 1. So 1/2 is equal to square root of b. If I square both sides, I have 1/4 is equal to b. So then that means my equation is y is equal to square root 1/4 x which if I simplified that, square root of 1/4 is 1/2, so it would be y is equal to 1/2 x, and that's where I get the exact same equation. So it's to show algebraically that the two equations are equivalent. So b, if I finish this off, I have square root of 1/4 times square root of x, so y is equal to 1/2 square root of x. C says, what is the equation of the curve reflected in each quadrant? So in quadrant 2, that means I want this one. So it's reflected over the y, so that means that my a has to be negative. So reflected in the y, so that means, sorry, I said my a, should be my b needs to be negative. So this would be the equation y is equal to, now it doesn't matter which one you're going to use, let's use this one, so this would be square root, sorry, 1/2 square root of negative x, or y is equal to negative 1/4 square root of negative 1/4 x. I want to reflect it, so let's do quadrant 4, because that one's a little bit easier. So this is reflected in the x-axis. So it's my y value then that I need to change from one to the next. So my a has to be negative, so this would be y is equal to negative 1/2 square root x, or y is equal to, sorry, negative square root 1/4 x if you're looking at a horizontal stretch. So then quadrant 3, that's the one that's going to happen over here. So this is, I want it going like this, so it has to be both. So I have to then have y is equal to negative 1/2 square root negative x, or y is equal to negative 1/4, or square root of negative 1/4 x. The company estimates its cost of production using the function Cn is equal to 20 square root n plus 1,000, where C represents the cost in dollars to produce an item. Describe the transformations of this function to C is equal to square root of n. So for this one, so for A, you're going to have a vertical stretch of 20, and graph is going to be translated up 1,000 units. So then it says, graph the function using technology. What does the shape of the graph imply about the situation? So if I put this into my equation, I might have to, oh, I don't have to, okay. So it's going to be 20 second square root of x, and then move your cursor over so you're out of the radical, plus 1,000. So from before, I know that that k value is going to affect my range. So when I go into my window, it's just at 10, going from negative 10 to 10, negative 10 to 10, but I know I have to move it up that 1,000 already, so there's no use even having this negative, my y minimum at negative 10. I can leave my x there, but let's put this to, I don't know, I'm just going to guess 100. X scale, let's go up by tens. this one though, we don't need a negative, so you can just start it at 0 if you want. Let's go to 2000 on here, and we'll go up by 100. I'm not sure how good of a graph that'll be, but we'll see. So if I hit graph, you kind of get the gist of it. It doesn't give you a very pretty curve on there. So what does the shape of the graph imply about the situation? Well, it's a little bit hard to tell from the graph, but it is going like this. So this would be the point here at 1000, and it's going like that. So, well, I just curved down, but I shouldn't have. So it's going like that. So basically it's saying that the cost of production is eventually, it's going to become less and less and less the more you do. You're going to have a base cost that you need to recover, and then eventually it's just going to almost become a straight line, but it's still going to have a little bit more increased cost. So it says interpret the domain and range in this context. Well, your domain is going to go from 0 to, it's going to be, instead of real numbers greater than or equal to 0, your range, whoops, it's going to be everything greater than or equal to 1000. Expected costs to produce 12,000 items. So that's when your n is equal to 12,000. So easiest way to do this is just to substitute in the 12,000 in there. If you're going to use your technology here, I didn't put my value to 12,000 in my window. So I would need to change that so that even if I said it was, say, I'm going to do 12,200, and I'm going to go up by 100. So what you can do then is in your second graph, this is producing 12,000. Nope, can't do it that way. So what I need to do is calculate, calculate. I want to find a value. X is equal to so your Y is equal to $3,190. So you could expect the cost to be almost $3,200. Okay. Second way of doing that is just to substitute 12,000 into there. And let's see how close we are. So if I go square root, oh, second square root, there we go. 1, 2, 3. 109 times that by 20. Oh, why do I have 2? Times 20. There we go. Plus 1,000. 3190. So we get the same value. Okay. So the last part is just the little key points on the last page here. So it says the radical function y is equal to square root of x is the base function. Basic characteristics, left endpoint at 0, 0, no right endpoint, meaning it goes on forever. Shape of half of a parabola. Your domain is all real or x is greater than or equal to 0 for all real numbers, and y greater than or equal to 0 for range for all real numbers. It says you can graph the function of the form y is equal to a square root b times x minus h plus k by transforming that base function. And then it says you can analyze transformations to identify the domain and range of the function based on that form. So your h affects the domain, k affects the range. So your questions are there to work on.